Hello everyone, welcome to the lecture. In the last lecture, we've learned the density law and one-dimensional flow through soil. Today, we focused on the two-dimensional problem. The Laplace equation and the flow net will be presented in this lecture. In the two-dimensional flow, the density law is still valid, and the flat is assumed to be incompressible. For flat flow problem shown in the figure, the inflow and outflow can be expressed in equation 1 and equation 2. Based on the law of mass conservation, the inflow equals outflow, then equation 3 will be derived. According to Dusty's law, the velocity equals coefficient of probability times hydraulic gradient. Vx and Vz in equation 1 can be expressed as equation 2 and equation 3 respectively. Then we substitute equation 2 and 3 into equation 1. Equation 4 will be obtained, which is used to analyze the flat flow in two-dimensional problems. For isotropic rock, we have Kx equals Ky. Then the flat problem can be simplified as equation 5, which is called Laplace equation. Laplace equation represents an infinite number of mutual perpendicular curves. One group of curves should pass of channels of water and called flow lines. Total head gradually decreases along a flow line. Another group represents lines on which the total head is constant and called equipotential lines. These lines are contours of constant total head. Flow lines are equipotential lines orthogonal. A selected number of flow lines and equipotential lines construct a flow net. The figure opposite shows the typical flow net. It is a graphical representation of the flow fields that satisfy Laplace equation and comprises a family of flow lines and equipotential lines. Flow nets are constructed for the calculation of groundwater flow and evaluation of heads in the soil mass. As shown in the figure opposite, the flow lines or streamlines represent flow paths of water particles. The area between two flow lines is called the flow channel or stream tube, and the rate of flow in the flow channel is constant. Meanwhile, the flow can't occur across the flow lines. An equipotential line is a line across which the total head at all points is equal. Flow lines and equipotential lines are perpendicular to each other. The difference between two equipotential lines is called the potential drop or head loss. The head drop between two adjacent equipotential lines is the same. To solve a two-dimensional flow problem in soil mechanics, the flow net sketching is required. There are 5 steps for sketching a general flow net. Step 1. Draw a structure and soil mass to a suitable scale. Step 2. Establish boundary conditions and draw flow line and equipotential line near the boundaries, in which the constant head boundaries represent initial or final equipotential lines, and the impermeable boundaries are flow lines. Step 3. Sketch flow lines by smooth curves, usually 3 to 5 flow lines. Step 4. Draw equipotential lines by smooth curves adhering to right angle intersection and the square grid conditions. Step 5. Continue sketching and readjusting until you get squares almost everywhere. Successful trials will result in a reasonable, consistent flow net. In most cases, 5 to 10 flow lines are usually sufficient. Depending on the number of flow lines selected, the number of equipotential lines will automatically be fixed by geometry and the grid layout. This is one example to show how to construct the general flow net for isotropic soil. After the flow net sketching, we need to use it to solve seepage problem in soil mechanics. Now, let's look at the flow channel in a flow net. According to the features of flow net, they had log delta H between each consecutive pair of equipotential lines equals the head difference between upstream and downstream sides. Delta H over the number of the equipotential depths ND. Based on Darcy's law, the flow rate in the channel equals the coefficient of probability times the cross-section area A and the hydraulic gradient. The hydraulic gradient in the flow channel equals delta H over the length of square element L. Then the flow rate can be obtained as shown in equation 1. Note that during the flow net sketching, the width and length are same so as to construct square elements. Therefore, B over L equals 1 for each of the elements. If the number of flow channels in the flow net equals NF and the total flow rate of the flow net equals the summation of flow rates in the flow channels, which equals the coefficient of probability times the total head difference between the upstream and downstream sides, and times the term NF over ND as shown in the equation 2. There are 6 steps to obtain the port pressure at any point in the flow net. Step 1. Select the datum. Step 2. Calculate the total head at upstream and downstream, which are HU and HD. Step 3. Calculate the total head drop between each consecutive pair of equipotential lines using equation 1. Step 4. Calculate the total head at J by equation 2, where NdJ is the number of equipotential drops at point J, and NdJ can be fractional. Step 5. Calculate the pressure head at J by subtracting the elevation head from the total head based on equation 3. Step 6. Calculate the port pressure Uj using the unit weight of water times the pressure head obtained in step 5. As for the two-dimensional problem shown in the figure, a sheet pail wall supporting 6 meters of water, you are required to draw the flow net, determine the flow rate if K equals 0.0019 cm per second, and determine the port pressure distribution on the upstream and downstream faces of the wall. Step 1. Draw the structure and soil mass to a suitable scale as shown in the figure below. Step 2. Find the number of equipotential drops ND and the numbers of the flow channels NF. In this problem, ND and NF equals 10 and 4 respectively. Meanwhile, the total height difference between upstream and downstream obtained at 6 meters. Then the flow rate can be calculated based on equation 1. Based on the method introduced in slide 14, the port pressure distribution on the upstream and downstream faces of the wall will be obtained as demonstrated in the table below. That's all for today's lecture. Thanks for listening.